Hey, what's up, my chem peeps? What in the heck are we going to do in this video? We're going to explain how the shapes of molecules are accounted for by hybridization theory. Two things we're going to do. We're going to define sp3, sp2, and sp hybridization. And two, we're going to determine the type of hybrid orbitals formed for atoms involved in covalent bonding. Alright, so to start, just recognize that as two atoms approach to form a covalent bond, the half-filled valence atomic orbitals, generally s and p orbitals, on each atom interact to form molecular orbitals. In other words, the atomic orbitals on the atoms interact to form molecular orbitals in the molecule. And recognize that atoms come together to form bonds because the potential energy is decreased when those molecular orbitals contain a total of 2 paired electrons compared to the separate atomic orbitals containing 1 electron each. The whole goal of bonding is to decrease the amount of energy used. And just to keep you on your toes, here's a thrilling image that describes how two atoms come together to form a bond. The important takeaway for this vid is simply to recognize that energy is reduced upon the formation of that bond. Now, we have something called hybridization theory that describes the mixing of 2 or more atomic orbitals of similar energies on the same atom to produce new orbitals of equal energies. Note that hybrid orbitals are orbitals of equal energy produced by the combination of 2 or more orbitals on the same atom. And the number of hybrid orbitals produced equals the number of orbitals that have combined. Now, we're going to start with what's called sp3 hybridization. In this instance, we combine one s atomic orbital with 3 p atomic orbitals to form a total of 4 sp3 hybrid orbitals. Check out this thrilling animation that shows the mixing together of 1s and 3p orbitals to form 4 sp3 hybrid orbitals. Woo! Magic! And recognize that it's the hybrid orbitals that account for those geometries that we see in the molecule. sp3 hybridization give us that tetrahedral shape. Take a moment, study this thrilling image that's in your notes. For sp3 hybridization, you're combining an s and 3p orbitals to form a total of 4 sp3 hybrid orbitals. We also have what's called sp2 hybridization. Here we're going to combine one s orbital with 2 p orbitals to form 3 sp2 hybrid orbitals. Let's do it. This time we're going to take 1s and 2 p orbitals, mix them together to get 3 sp2 hybrid orbitals. Again, it's the hybridization theory that supports the molecular geometries that we observe of the different molecules. Check out the thrilling image you've got in your notes. For sp2 hybrid orbitals, we're taking 1s and just 2 of the p orbitals to form 3 sp2 hybrids. And then lastly, we've got sp hybridization. Here we're combining one s orbital with one p orbital to form 2 sp hybrids. Check it out on the simulation. 1s, 1p, mix them together and form 2 hybrid sp orbitals. This type of hybridization is what gives us our linear geometries. Notice we're taking an s orbital and a p orbital, mixing them together and getting 2 hybrid sp orbitals. So, how do we determine then the hybridization about an atom in a molecule? Simply a matter of counting the number of regions of electron density. 4 regions, that means the atom is sp3 hybridized. 1s plus 3 p orbitals equals 4. Oh, 4 regions, sp3 hybridized. But what if you have 3 regions? If you count 3 regions, that means that it's sp2 hybridized. You've taken one s orbital, mixed it together with 2 p orbitals to form a total of 3 sp2 hybrid orbitals. Finally, sp hybridization is when you have 2 regions of electron density about the atom in the molecule for which you're trying to determine its hybridization. 1s plus 1p gives you 2 sp hybrid orbitals. So again, just count up the regions of electron density and then think to yourself, what would the sum of the superscripts be in your 3 different types of hybridization that you have to know? Easy. Let's determine the hybridization of boron in a molecule of BF3. All you have to do is count up the regions of electron density that surround that atom. In this case, there are 3 regions, which means the boron is sp2 hybridized. Boom. 1 plus 2 equals 3 regions. All right, now that is pretty much all you need to be able to do. But let's think a little deeper about what's going on with this molecule. If boron is sp2 hybridized, we're going to take one s and 2 p orbitals, mix them together, and make 3 hybrid sp2 orbitals. Slightly more energy than the 2s, but less energy than the 2p. Again, our goal here is reduce the amount of energy. And then notice how this will help us better understand the geometry of BF3. You can think of these electrons then, each occupying one of the sp2 hybrid orbitals. And then each fluorine, which needs just one electron to complete its valence level, will slip in and form a bond completing one another's orbital. We'll say that this here represents this bond. Then I'm going to get rid of some of this so it's easier to understand. Another fluorine. So this sort of sneaks in here. It's a little tricky to do. And this represents this fluorine. And then we've got a third fluorine. Oh, and again, a little tricky here, but notice how this fluorine would be represented over here. All right, so that's a little bit intense. I want to practice just a couple more where you are simply going to identify the type of hybridization. Let's keep it easy. Carbon dioxide, I've got 1, 2 regions of electron density about the central carbon. So this would be sp hybridization. Boom. 2 regions of electron density. 1 plus 1 equals 2. 2 regions. How about C2H2? This carbon has 1, 2 regions of electron density. So the hybridization about this carbon on the left, sp hybridization. Carbon on the right, 1, 2 regions of electron density. Also sp hybridization. Boom. All right, that does it for this vid. Have a fantastic day.